Okay, so thank you for inviting me to be part of this workshop. I will present my work on the topic of active learning and information seeking in infancy. So a lot of this work has already been published, and some of you have probably heard me talk about it before. I apologize to those who have. I will present some of my old work spanning from my PhD, looking at infants as active learning in social contexts, using both behavioral studies and neural indices. And then towards the end, sort of the last third, I also present some ongoing work looking at using the same kind of measures of active learning in non-social contexts of causal reasoning. Okay, so starting with the social learning, it has long been acknowledged that in order to ensure rapid and efficient transmission of information between people, both partners of a communicative exchange should be actively involved. If the learner is able to take on an active role in gathering information, they don't need to passively rely on information being provided. And a number of infant behaviors, such as social referencing, babbling, pointing, selectivity, and social partners, could plausibly serve the function of infants actively eliciting and modulating the information that they receive from others. Indeed, studies have shown that babbling and pointing, for example, have an effect on infants' knowledge acquisition, with more vocalizations and pointing predicting better subsequent learning outcomes. And while this relationship has been predominantly explained by infants' behavior creating more opportunities for social interactions, hence facilitating infants' learning due to the increased amount of information they receive, it is plausible that in addition to modulating the amount of information infants receive, responding to expressions of interest that we believe these are may facilitate their learning because they signal when infants are interested in learning something new and what they're interested in learning about. The reason why we thought that it would be interesting to look at possible behaviors expressing interest in infants is because many studies in adults have shown that there's a strong relationship between interest or curiosity and learning. We know that it's interest or curiosity as much as IQ that predicts academic achievement, and we know that states of curiosity or heightened interest can function as an intrinsic rewarding mechanism. Importantly, in studies such as that by Gruber and colleagues, in which they elicited states of curiosity by asking participants trivia questions, it has been shown that the degree of interest or motivation to learn prior to receiving information can directly modulate how much of this information will actually be retained. And while direct assessments of curiosity in infants are not feasible, some infants' behavior appear to be consistent with what would be predicted based on theories of interest or curiosity-driven learning. For example, even in their first year of life, infants allocate their attention in a way that maximizes information gain. And in the same way as adults do, infants guide their exploration towards closing gaps in their knowledge. And the learning appears to be boosted when their curiosity has been piqued, such as following an unexpected event. So this suggests that the rewarding systems of information search and consumption may already be in place in infancy. And unlike adults, infants' interest or motivation to learn may directly affect what infants will learn in any given moment. And therefore, given the impact that feeding curiosity in infants may have on their learning, and the fact that learning from others is probably one of the most prominent modes of learning for infants, a research aimed to investigate what role infants' interest or motivation to obtain information may play in the domain of social learning. And we reasoned that if a behavior is functioning as an information-seeking tool, then we should expect it to be modulated by the availability or need for information and for it to be involved in learning. And the first behavior that we investigated in my work is the gesture of pointing. So our question was, do infants point in order to request information from social partners? And there's a lot of evidence that suggests that this may be the case. Infants point more when there's novel objects than familiar. Adults' most common response to pointing is labeling and providing information. Amount of pointing predicts vocabulary growth, and it is in fact the reference towards infants, towards which infants point, that are most likely to enter their vocabulary. To illustrate how infants express interest through pointing and the kind of responses they receive, I just want to show you a short video. This is from a free play interaction between an infant and a parent. So the baby is 16 months old.
He's got 2 humps. 1 hump, 2 humps. The camel. I don't think you've ever seen one. That's a bird, isn't it? Parrot. And there we are. Yeah, that's the little fish. Up, up, up. We're going to see some fish in Scotland. That's right. There's the flower. That's the bee.
So it's clear from this video alone that the adult is not the only one directing the interaction of information exchange. In fact, it's the infant that seems to be in charge. And if adults like this mom interpret and respond to this kind of gesturing with information, it's clear that this gesture of pointing could serve as a powerful learning tool. And infants could use it to express interest even before they can verbally ask questions. So our first question was, do infants request information when pointing? And we reasoned that if pointing serves the function of obtaining information, then it should be modulated by the availability of information. So the way we manipulated that is we had one group of infants interacting with a knowledgeable informant, labeling familiar objects correctly, and another group of infants interacting with someone who consistently mislabeled objects that infants knew. And while the experimenter and the infant played with these objects, novel and familiar objects were appearing from behind the experimenter. So this is what the scene looked like. So if the infant wanted to direct the experimenter's attention to the novel objects appearing behind her, they would have to point. And the reason was that if pointing serves obtaining information, so that if infants request information by gesturing through pointing, then they should point less when they interact with someone who is not able to provide them with reliable information, namely someone who mislabels objects that infants are familiar with. And this is indeed what we found. So the group of infants who interacted with an adult who was correctly labeling objects pointed twice as much as the ones interacting with incorrectly labeling adults, which suggests that infants modulate the amount of information seeking based on the reliability of the source available. Our next question was, do infants in fact learn the information that they request? And following the reasoning from adults, that is, if pointing truly signals interest or curiosity about the object that they're pointing to, then the information that we provide in response should be better assimilated than the information that we provide unsolicited. To test this, we created a situation in which infants were offered two novel objects at the same time, and were given an opportunity to point to one of them. And we took that as an expression of interest. And once infants had made the choice, the experimenter then demonstrated the function of either the object the infant had pointed to or the object the infant had not pointed to. So this looked like this.
How about these two? You like this one? Good job. Look, I'll show you how it works. How about these two? Look. You like this one? Let me show you how this one works. Look, you can look through it. Wow. Did you see that?
So all the objects that we presented children were novel, and all the functions that we showed them were arbitrary, so they didn't have any functional relation to the objects. And after we have demonstrated the functions of all the objects, two of the ones they chose and two of the ones they didn't choose, we then tested how well they remembered the functions that were demonstrated by testing whether they replicated any of the functions that look like this.
That's right. This one. Do you remember that one? What do you do with it? Henry, can you show me what you do with it?
Okay, so what we reasoned was that if infants' requests for information through pointing are expressions of interest, then information received in response to them should be better assimilated. And this is indeed what we found. So the functions of the objects that the infant had pointed to were replicated significantly better than the functions that were shown on objects the infants had not pointed to. So our results are consistent with the idea that curiosity or interest, as expressed through interrogative pointing, facilitates the encoding of information. However, with these results alone, we couldn't conclude whether infant learning was in fact facilitated when the requests were responded, or whether it was hindered when the requests were not responded to. To do that, to control for that, we ran another experiment in which one group of infants received all their choices responded to, the other group did not have a choice in which object they were shown. And what we found was that it seems that indeed it is, pointing has a facilitative effect on learning, in that functions that are shown on objects that are pointed to are remembered better than ones that are not solicited. Okay, so based on the fact that infants modulate the amount of pointing according to reliability of information that they can receive, and that it is clearly involved in learning, we can conclude that pointing is indeed a form of active social learning in infancy. And it appears to reflect, so we assume that when infants point, they are perhaps in a sort of optimal state for learning. They're signaling to people around them that they're prepared to learn and what they want to learn about. So our next step in our exploration of infant active learning was to try and find a neural correlate of this optimal state for learning, which we could use to elucidate what infants' expectations or motivations are in different social learning contexts without having to rely on behavioral expressions of interest. For this, we turn to adult research, where many studies have identified oscillatory activity in theta frequency band as involved in learning and potentially reflecting a sort of strategic preparatory state for learning. I will talk more about this in the workshop, but just briefly, studies in adults have shown that the level of activity in theta band during encoding predicts the rate and accuracy of recall. When adults can predict when the stimuli will be presented, theta activity was observed in anticipation of the presentation, and this anticipatory activity has been shown to predict the degree to which stimuli was subsequently recorded. And importantly, is modulated by the participants' motivation to learn information they're expecting to receive. So in short, when adults can expect to receive information and are motivated to encode it, this intent is reflected in theta activity before information is presented, and this activity leads to superior learning. At the time, there were fewer studies reporting theta activity in infants, but there was some evidence that suggests that theta might be involved in learning also in infancy. For example, there were studies showing more theta activity when infants were listening to infant-directed as opposed to adult-directed speech, when they were exploring objects, following a violation of expectation, all of which are situations often learning. But has shown directly whether there is a relationship between theta and learning in infants. So that is what we set out to do, reasoning that if theta activity is involved in learning in infants as it is in adults, then we should be able to predict infant. And to do this, we had 11-month-old infants freely exploring 8 different objects of various complexity while we were recording their EEG activity. Each object was explored for maximum 40 seconds without any interruptions from the experimenter or the parent. And after this exploration, infants' memory for the objects was tested using a preferential looking task. So what infants saw on the screen were the objects that they explored combined with objects that were very similar, but had one featural change in their appearance. So the reasoning here was that if infants had encoded the features of the objects they had explored previously, then they should notice that the other one is slightly different and might show a looking time preference. In contrast, if the object's features were not encoded well, then both of the objects should be equally familiar or novel, and therefore their looking behavior should be equal amongst the two. So what we wanted to look at is whether the amount of theta during the exploration of the objects would in fact predict whether or not the objects would be later recognized the test. And what we found was a significant positive relationship between the difference in theta during the exploration of objects and the difference in looking time preference at the recognition test. So having established that theta oscillations are predictive of learning also in infants, We then utilized this measure in our exploration of potential information-seeking behavior in infants. And the next behavior we explored is social selectivity, that is, infant selectivity in choosing which social partners to attend to or interact with. So just to give you a bit of background on the literature on infant social selectivity, many studies show that infants are selective in their social interactions. For example, we know that things like whether or not someone is looking directly at them, speaking info-directed speech, whether someone is competent and reliable, influence the degree to which infants will attend to these social partners, follow their gaze, imitate their actions, how willing they are to interact with them, and so on. And we also know from another branch of research that all of these infant behaviors are also influenced by other characteristics of social partners, such as whether the partners speak the same language as the infants or are the same race, whereby infants display preferences to attend to, imitate, and so on the social partners that could be defined as belonging to the same social group as infants. And while this first set of behavioral biases has been suggested to potentially serve the function of ensuring infants learn from social partners that are willing to teach them, the behavioral preferences the infants demonstrated for native speakers, for example, have in contrast been interpreted as infants dividing the world in social groups and guiding the behavior according to a principle of in-group loyalty. What we instead proposed is that infants' preferences for others exhibiting cues to same group membership may in fact reflect the same strategy of directing attention towards the best sources of information. Because if you think of it, allocating attention to someone speaking the same language may indeed be a good learning strategy, given that the information that they provide is something that you can understand, first of all, and that the common language typically indicates shared culture and common knowledge. So to ask whether infants are indeed perceive native speakers as superior sources of information, which might explain their behavioral biases, we studied whether infant social preferences are associated with an expectation of information. So we again use theta oscillations, which we have now shown that they predict learning in infants as they do in adults. However, theta in the study that I just described was recorded at the same time as infants were already encoding information, so while they were exploring the object. But the most interesting aspect of adult studies for our question here was that the increase in theta was evident before the stimuli was presented. And since it was modulated by the adult's motivation to learn, it implies that theta reflects some sort of active preparatory state to encode information, a state that perhaps infants are in when pointing to an object and awaiting information in response to their gesture. So if you want to explore whether infant social preferences are driven by whom they can expect to learn from, we first need to demonstrate that theta is in fact present in anticipation of receiving information in infants, and that it is selectively present when information is available. So with the next study, we manipulated whether infants can expect to receive information from a social partner or not. We did this by introducing them to two models on the screen. One of them we called informative, the other non-informative. The trials look like this. So following a baseline, a person appeared on the screen, looking directly at the infant and smiling, then shifting the gaze to the object in front of them. These were all novel objects. And following 2 seconds of them just gazing at the object, the model would provide information in one case, or in the other case, this would within subject comparison, the same thing would happen, except that at the outcome phase, the person would not provide any information of the novel object. And this information was either a label for the object or its function. And the period of interest was the time when actually nothing was happening on the screen. So when the informants were silent and still, but based on the familiarization trials and over the course of the test trials, infants should learn that they can expect information from one of them and not the other. So if theta oscillations reflect information expectation in infants as they do in adults, then we should see more activation during the anticipation period of the informative compared to the non-informative conditions. And this is indeed what we found. So just to orient you on this complex graph. So on the left, we have the informant trials, on the right, the non-informant. The top part is frontal electrode location, and the bottom is bilateral temporal. And what we see is this darker red activation signals more activity in the theta frequency band in the informant trials on both recording sites compared to non-informant trials. And on the right, the same data is represented with bar plots. So having established that theta is modulated by the potential of social partner to convey information, we can now return to the question of infant social preferences. And we use this measure to ask whether infants perceive native speakers as better sources of information than non-native speakers, which may explain their behavioral biases. So the paradigm was identical to what you have just seen, only that the informant and non-informant were labeling the novel objects in either infant's native speech or a foreign tongue. So if infants do expect information from native speakers, but not foreign, which would explain why they show behavioral biases for native speakers, we should see the same pattern of activation as in the previous conditions, and that is indeed what we found. So you can see that the activity in the theta band is almost identical when we compare native speakers to the other informant conditions and non-native speakers to the other non-informant conditions. So our results suggest that infants indeed treated native speakers in the same way as the informative and non-native as non-informative. And relating these results to other previously mentioned behavioral preferences that infants show towards people who appear willing to teach them and provide reliable information, we argue that these results suggest that infants' behavioral preferences towards native speakers could also be reinterpreted as driven by their motivation to learn as opposed to social preferences. And this proposal also leads to another prediction, namely that if information provision is the main reason for why infants choose to attend to and interact with native over foreign speakers, then it should be possible to manipulate this bias by, for example, exposing infants to an informative foreign speaker. So these are two studies that I'll now present following up on this study that are not published. So our first condition aimed to look at whether if we make both the native and foreign speaker equally informative, would infants still discriminate between the two based on language? To do this, we designed a study in which the native-foreign contrast was established in familiarization and reinforcement trials, where the two speakers were speaking the respective languages and labeling familiar objects. And then in test trials, the infants again saw only one of the two speakers, and the trial outline was the same, except now in the outcome period, both of the informants would show the function of the novel object. So crucially, this kind of information is obviously nonverbal. So they don't speak, but they just demonstrate the function, which means that it's equally intelligible to learn this information from foreign and native speakers. And therefore, we might expect similar kind of learning processes despite the language. So again, we looked at the anticipation period when nothing is happening, and we can measure whether infants engage theta oscillations prior to receiving information. So if infant selective preparation to encode from information speakers, from native speakers observed in previous findings is based on information gain, then we may be able to overwrite this preference by teaching infants that they can expect information from foreign speaker. And our results showing that they show equal amount of theta for both native and foreign speaker indeed suggests that when equal information gain is possible from native and foreign speakers, infants are no longer show a preference, but appear equally willing to learn from both. And then we took a step further, where we try to actually pit the information provision against the language group directly. So we reasoned that if we teach the infants that in this particular situation, it's the foreign speaker that's more informative than the native, which of the two, spoken language or information provision, will influence infants' behavior and activity, neural activity more. So again, the same paradigm, except in this case, it was the foreign speaker that demonstrated the function, whereas the native speaker did not, just picked up the object and looked at it. So again, language group established separately in the test trials. all information is nonverbal, but it's only the foreign speaker that gives any information. And we look at the anticipation period, and we wanted to see whether the preference in preparing to learn from native over foreign speaker will be reversed. But what we found was, again, no difference. So infants seem to be equally engaged with native foreign speaker, even though the native speaker was not informative. So it seems that infants have default expectation of information provision from native speakers, which was demonstrated in a first set of studies, and it seems that this expectation can be overridden with this relatively short experimental evidence. However, importantly, both of the last two studies do show that if the foreign speaker is shown to be informative, infants do show preparation for learning also from foreign speakers. But how does this expectation of information and willingness to learn from foreign speakers influence infants' behavioral preferences for these speakers? So our reasoning was that if the possibility to learn from social partners is truly what drives infants' behavioral preferences, as shown in other studies, then we should expect these preferences to go away once a foreign speaker is demonstrated to be informative. So we did test this by following up the EEG experiment with the classic behavioral task in which infants show preference for native speakers. This was originally run by Kinsler et al. And in the original study, they had a foreign native speaker present one of two identical objects each on the screen, and then the real objects appear in real life in front of the infant, and they measure which of the objects the infant approaches, the one that offered by the native speaker or the one offered by the foreign speaker. And what they find is a strong preference to approach the native speaker's object, which was interpreted as reflecting in-group bias. But according to our hypothesis, this preference could instead be reflecting infants' bias to interact with people they can learn from. And in which case, if we have the same speakers that we had in the EEG task at the end offer the objects, so now in this task, it's the foreign speaker that is more informative than the native, then this behavioral preference should go away. And indeed, what we find that as a group, infants did not show a preference for choosing the object offered by the native speaker. If anything, numerically, more infants chose the object offered by the foreign than the native speaker. So taken together, these studies suggest that although infants have a default bias to treat native speakers as better sources of information, changing infants' expectations regarding the information provision from foreign speakers by teaching them the foreign speaker is informative results in infants being willing to both learn as well as interact with foreign speakers to the same extent as native. And in light of these studies, we could argue that the previously found preferences for native speakers may have been due to an imbalance in information provision and not affiliation. Okay, so now shift gears a bit to non-social context and tell you about some ongoing work looking at active learning in using the same kind of measures in the context of causal learning. So I find the question of causal reasoning interesting because seeking explanation and uncovering causal relationship is a potentially uniquely human type of curiosity. While other animals explore the environment and seek information in service of finding shelter or food, and they're also very good at solving tasks, there's currently no evidence that would suggest that animals deliberately seek causal explanations or strive to understand the causal structures in their environment. Humans, on the other hand, seem to seek explanation and deliberately uncover causal mechanisms, and we do so spontaneously and from a very young age. Not only have children been shown to distinguish genuine cause from spurious correlations, when given ambiguous evidence, preschoolers spontaneously select and design informative interventions to reveal the causal relationships between the objects that they're engaged with. And while several studies have shown that children are sensitive to whether the evidence they observe is confounded or not, and that they actively seek and generate disambiguated information, less is known about this process in infants. Before the age of 2, infants have limited means on acting on the world themselves, And much of their learning therefore depends on observing other people's interventions and trying to make the right conclusions. So the aim of our study was to investigate if infants exhibit any sensitivity to whether information that they are observing is confounded or not. In other words, can we find evidence of infants recognizing situations in which they're about to receive a piece of information that is relevant for a causal inference? And if so, does this anticipation of information predict whether or not they will successfully infer the correct causal structure? So to do this, we adapted the classic Blicke detector task, and we taught infants a causal relationship and a sorting rule. There were two types of familiarization trials. I'll show you an example.
Hi, baby. Look at this. Wow.
Okay, so in this case, you saw that the object activated the machine when placed on top of it. Following the effect, the green box lit up and the girl sorted the object into the green box. In another type of familiarization trial, a very similar thing happens, except that when the girl places the object on the machine, no effect is seen. So the machine stays silent and no lighting is seen. And in this case, the opposite box would light up and the girl will place the object in that box. Of course, the pairings between sides and effects were counterbalanced, but to simplify, we'll focus on the condition in which objects that triggered the audiovisual effects are sorted in the green box, and the objects that do not trigger the effect are sorted into the orange box. Then we have another type of familiarization trials, which the girl shows what happens when she places two objects on the machine at the same time. In this case, the objects are taken from the boxes and know that they're now marked with the corresponding colors so as to help infants track which is which. And they see examples of two green objects being placed on the machine and the machine produces the effect, two orange objects and no effect, and finally one of each, in which case, again, they see the effect. So this is the evidence that infants receive. And what we hope they learn is that whenever there is at least one green object placed in the machine will always activate. If there are only orange objects placed, the machine never activates. And then in the crucial test trials, infants see repetitions of trials in which the girl places a new unmarked object on the machine together with one of the pre-sorted ones. So an example looks like this.
Hi, baby. Look at this. Wow.
Okay, so in this case, the object was paired with a green one. And following the effect, the girl pauses with the new object in the middle. We hear the sorting cue sound, but none of the boxes light up and the girl does not sort the object anywhere. The same thing happens if the object is paired with an orange one. So in this version, in the test trials, the effect is always present and the trials always end with the girl holding the object in the middle. As you may have noticed in the video, we have an anticipation period where the girl is holding the objects above the machine, but before they actually are in contact. Then the second period I'll refer to as the inference period. This is when the infants are seeing the effect and they can make the correct conclusion. And finally, we have the prediction phase in which, importantly, the girl does not sort the object, but we want to see whether the infants actually predict where it should go. Now, what we measured is, in order to find out whether infants are sensitive to whether the information is confounded or not, we measure theta oscillations, again, the same neural rhythm, which has been shown to indicate infants' expectation of information and is involved in learning, and to test whether they make the correct inferences about whether the unmarked object is one that produces the effect or not. We look at infants' eye movements to the two boxes in the prediction phase. And finally, we wanted to investigate whether infant sensitivity to confounded information, as reflected in theta activity, would be predictive of whether or not they would make correct predictions at the end of the trial. Here's what we predicted on the timeline of the trial for the different measures. So when the object is paired with a green one, as is the situation at the top panel, this situation doesn't allow infants to learn anything new about the new object. We already know that the green object alone makes the machine activate. So the effect that follows is not informative about the function of the object. In other words, this is the confounded information condition. In contrast, when the new object is paired with the one from the orange box, as it is the case below, infants should know that the orange one alone will not activate the machine, so they can expect to learn whether the new object is active and which box it belongs to. In other words, unconfounded information. We will measure whether infants hold such expectations by measuring their theta activity during this period. And we predict more theta activity in the anticipation phases of the trials where unconfounded information is presented compared to the confounded trials. And following anticipation, we have the inference and the prediction phases. And during the prediction phase, we look at infants' eye movements to see whether they anticipate where the unmarked object should be placed. And again, the bottom situation in which infants received unconfounded information allows for infants to make an inference about whether the unmarked object belongs to the green or orange box. And they should anticipate that the object should go in the green box because the effect cannot be explained by the orange object. In contrast, where the causal role of the unmarked object remains ambiguous, because the effect can be explained by the presence of the green object alone, infants should not be able to infer where the object should be sorted to and should therefore be looking at chance or making no predictions. So, So we will first look at the theta activity in the anticipation phase, where, if you remember, we expect to see more theta activation and expectation of unconfounded than confounded information. We have collected 34 infants between the ages of 15 and 17 months of age. And what we see is, so to orient you, this is, again, the frequency plot spanning from 1 Hertz to 10 Hertz, with theta roughly between 3 and 5. And so this is the confounded condition. We can see there is some theta activation also in the confounded condition, but this activity is stronger in the unconfounded trials. So with this first set of samples, this is the theta range. We found a significant effect of frontal theta activity in anticipation, in that it was stronger activity in the unconfounded than confounded information. So we find sensitivity to whether information that infants are receiving is confounded or not in 15 to 17-month-olds. Unfortunately, in this paradigm, we were not able to elicit any predictive looks. In fact, only about 20% of the trials had predictive looks, so the analysis couldn't really be meaningful. But because we really wanted to look at whether the EEG data relates to predictions, to look at subject by subject differences, possibly also trial by trial, we designed the second version of the study. So in the new version, what we do is we have more familiarization trials, double in fact. And importantly, because of the ratio of familiarization versus test trials, in the original study, there was only about 1/3 of the trials where the girl actually sorted the object into the boxes. So it's not surprising that the infants were not predicting, whereas in this case, it's 2/3 of the trials where they see the sorting, and only 1/3 of the test trials where they don't. We also added additional cues before the sorting happens. So now the trials looks like this. It's in Danish because it's now running.
Med dig, se den her. Wow.
So the difference here is that first, both of the objects light up, and only once she places the object into the box, the second one lights up. This was done because it was clear that most infants just kept staring at the girl's face during the prediction phase. And this way we sort of tried to grab their attention to look at the boxes to see whether they actually look systematically between the two boxes. And the other crucial difference is that we added another type of test trials. So in the unconfounded test trials where the object is paired with one that doesn't work, half of the test trials now don't show the effect. So this is the non-functional pair, and there is no effect.
Wow.
And again, in test trials, there is no sorting, but both boxes first light up, and then we hear the second sound cue that would indicate the object being placed in the box. The rest of the measures and predictions are the same. And so now, if we look at the looking time, this version actually successfully elicited predictive looks with at least one fixation in the areas of interest surrounding the boxes detected in more than 90% of the trials. So if infants are making correct inferences, we should be able to capture it. I have here an illustration of the gaze from one trial. So in this case, it's the trial you just saw where the object was paired with the non-functional and no effect. And so the correct predictive look would be to the orange box. So in this example, this fixation to the orange box would be scored as correct. If a fixation would be made to the opposite box, it would be scored as incorrect, -1. And if there's valid data but no prediction, the look is scored as 0. And average across test trials, this would give us looking scores, which if they're larger than 0, would systematically correct predictions to the right box. Whereas if they're 0 or negative, it would mean that we have no evidence that infants are making correct predictions or correct causal inferences. And crucially, we only predict that infants would make any systematic predictions in the unconfounded trials, as no prediction is in fact possible in the confounded trials. And moreover, because in the new version of the unconfounded test trials, we have ones that no effect is seen on the music box, which means that in half of the trials, the correct prediction is orange, and the other half of the trials, correct prediction is green. And we therefore control for any side biases that infants may show. And so if we look at the looking data, as I said, 90% of the, more than 90% of the trials actually had predictions. And what we see is that about, if we look at the first look averaged across all trials, we see that about 9 babies out of 24 make the correct predictions. So we also have other measures such as all looks, in which case it's 13 babies. We can look at the differential looking score. So I'm still exploring this data to see what makes more sense. But for now, I'll just focus on the first look since this is the most commonly used. And so these values reflect average across all trials. So any positive value means that in most cases, in most trials, they made the correct prediction. If it's negative, they were systematically wrong. But a third of the babies is basically a chance. And so if we look at the theta activation in the same kind of analysis as I've shown you in the previous version, so this is now 24 babies, so we're still collecting data. But what we see is, so now I only plot the theta band for 3 to 5 hertz. There's again some activity in the confounded, but stronger activity in the unconfounded trials. But crucially, because we now have predictive looking data, we can actually split the sample and look at only and compare the babies that make correct predictions versus the ones that don't. And what we see is that seemingly, visually, I haven't done the statistics yet because we're still collecting data, this difference between confounded and unconfounded is stronger in babies that make correct predictions. So to plot them all in the same, so this is all babies that make correct predictions, and babies that do not make correct predictions. So this is the anticipation period of the trial while the babies are waiting to find out whether there will be an effect or not and whether they can make the correct conclusions. And it seems that babies that end up making correct predictions show more sensitivity, a larger difference between in the anticipation period reflected in the theta activation being stronger in the unconfounded than confounded. So this suggests that they are expecting to learn in the unconfounded conditions, but not in the confounded, whereas this difference is not pronounced in the babies that do not make predictions. Similar pattern activity is also seen if we look at the phase where the effect is already seen. So babies can make an inference about the function of the novel object. And again, we see a seemingly stronger difference in the correct predictors. And just to note that it is the confounded condition where the babies always see the effect. So if theta activity was driven by perhaps the reward value of the effect itself, we should see more activity in general in confounded than unconfounded, but we in fact see the reverse, which suggests it does have something to do with learning and not just observing. Okay, so when 15 to 17-month-olds are given enough evidence, about 40% of them seem to make the correct causal inferences as evident in their predictive looks. When we compare the babies that made correct predictions to those that didn't, we can see a more pronounced difference in anticipatory theta activity. And this difference in theta activity implies that they are sensitive to whether the information that they are observing is confounded or not. And the sensitivity and selective preparation and selective learning may be the mechanism that underlies success in inferring the causal structure. And then more general conclusions for the talk. I hope I convinced you that infant pointing can be a tool for obtaining information and is deployed selectively according to availability of information, that responding to infants' requests for information leads to better learning, which is analogous to learning when curious as adults, that infants' selectivity in social partners may result from learning and not social preferences, and the theta oscillations are a useful measure to investigate infant active learning as they're directly involved in encoding success and may reveal the mechanisms underlying causal learning. With that, I thank you for your attention and invite questions.